Hi, my name is Jay Giblin, and I'm a fifth-year physical chemistry graduate student working with Dr. Ken Kuno here at the University of Notre Dame in the Department of Chemistry and Biochemistry. Our group focuses on synthesizing semiconductor nanowires and elucidating the basic optical properties at the single-wire level. In general, nanowires are cylindrical nanostructures that are crystalline and have diameters from a few nanometers to hundreds of nanometers and lengths between 1 to 100 microns. In our group, we use a method referred to as solution liquid solid growth to prepare our nanowire samples. Now, this preparation is actually similar to those of colloidal quantum dots, but in the case of nanowire preparation, we're introducing a low melting point catalyst particle. The synthetic setup looks something like this. First, you start with a Schlenk line, a 3-neck flask, a high boiling solvent like trioctyl phosphine oxide, a metal precursor such as cadmium oxide, and a fatty acid like octanoic acid. The acid cracks the metal precursor and forms a reactive metal cation compound upon heating to approximately 250 degrees Celsius. Then, in a syringe, a chalcogen precursor like trioctyl phosphine selenide and low melting point nanoparticles like bismuth are mixed together. Upon injection, the reactive precursors dissolve within the bismuth particles and quickly reach a supersaturated point where crystals nucleate in one dimension and additional precursors react at the liquid particle nanowire interface to form long, skinny nanowires. From an optical standpoint, nanowires are interesting because their absorption and emission properties can be tuned by varying their diameter. Specifically, ensemble measurements reveal that as nanowire diameters decrease, a blue shift in their onset of absorption occurs with a corresponding blue shift in their photoluminescence peak. To determine the absorption and photoluminescence properties of individual semiconductor nanowires, we use single-molecule microscopy and spectroscopy. These techniques allow us to perform confocal imaging, epi-illumination, and emission spectroscopy on single nanowires such as cadmium sulfide and cadmium selenide. What you are seeing here is a movie of a single cadmium selenide tripod nanowire taken under epi-illumination. During the course of the movie, the tripod is excited with linearly polarized light at 532 nanometers, and the orientation of the incident polarization is rotated with respect to the three arms. What you find from analyzing the movie is that any one of the three arms is brightest when the incident polarization vector is parallel to the arm and darkest when it is perpendicular. This is due to the fact that the absorption cross-section of a nanowire is largest for light polarized parallel to a wire's growth axis, and smallest when the light is perpendicularly polarized to the wire's growth axis. This means that as more light is absorbed by one of the three arms, as the polarization vector becomes parallel with a particular arm, the brighter the arm's emission becomes. In the perspective that Dr. Kuno and myself wrote, entitled Nanostructure Absorption, a comparative study of nanowire and colloidal quantum dot absorption cross-sections, we discuss how to model the absorption cross-section of a nanowire using both an approximate local field theory and rigorous Poynting vector analysis. Both approaches successfully model the observed polarization anisotropies, like you just saw in the movie. It's the strong polarization dependence of a nanowire's absorption that leads to scenarios that we discuss in this perspective, where the absorption cross-sections are nearly an order of magnitude larger for a nanowire than those of a quantum dot. The future is bright for semiconductor nanowires, and as researchers continue to understand their basic optical and electrical properties, their implementation into applications like next-generation solar cells and photodetectors will become an exciting reality.